Hello science enthusiasts, and welcome to this journey into the fascinating world of string theory. We're here to pull back the curtain on this complex theoretical framework and make it accessible. At its core, string theory is an ambitious attempt to reconcile all the forces of nature into one grand, unified theory. So buckle up for an adventure into the very fabric of reality. Join me as we unravel the mysteries of the universe through the lens of string theory. To understand why string theory is important, we first need to look at the current state of physics. In the world of physics, there are two major theories that govern our understanding of the universe. On one hand, we have general relativity, the brainchild of Albert Einstein, which beautifully explains gravity and the large-scale structure of the universe. On the other hand, we have quantum mechanics, a theory that describes the peculiar behavior of particles at the smallest scales. While each of these theories is successful in their respective realms, they are fundamentally incompatible. When we try to mesh these two theories together, we encounter serious problems and inconsistencies. It's like trying to fit a square peg into a round hole. It simply doesn't work. This is one of the greatest challenges in theoretical physics today. What we need is a theory of everything, a unified theory that can reconcile the macroscopic world of general relativity with the microscopic world of quantum mechanics. This unifying theory would tie together all the fundamental forces and particles in the universe into a single, coherent framework. This is where string theory enters the picture, promising a unified understanding of the cosmos. The roots of string theory can be traced back to the late 20th century. During this time, physicists were grappling with a mathematical conundrum. They were trying to reconcile the laws of gravity, described by Einstein's theory of general relativity, with the laws of the subatomic world, outlined by quantum mechanics. These two theories were in stark contrast, and attempts to unify them resulted in mathematical inconsistencies. A unifying theory, a theory of everything, was desperately needed. Enter string theory. The birth of string theory was neither straightforward nor intentional. It all began when Italian physicist Gabriele Veneziano was studying the behavior of strong nuclear forces, the forces that hold the nucleus of an atom together. Veneziano stumbled upon a mathematical formula that perfectly described these strong interactions. But there was a catch. The mathematics suggested that the fundamental constituents of matter were not point-like particles, as was widely accepted, but rather something much more unusual. This is where American physicist Leonard Susskind comes in. Inspired by Veneziano's work, Susskind proposed a radical idea. He suggested that the fundamental constituents of matter were not particles but tiny one-dimensional strings. These strings could vibrate, and the different modes of vibrations were perceived as different particles. Thus, all matter, all forces in the universe, could be explained as the harmonics of these tiny, vibrating strings. It was a symphony at the heart of existence. The concept was revolutionary, it was elegant, it was string theory, and it promised to solve the long-standing problem of unifying gravity with quantum mechanics. It was a theory that had the potential to explain everything, from the tiniest quark to the largest galaxy. But string theory was not without its skeptics. Many physicists were hesitant to accept a theory that seemed so abstract, so far removed from the tangible world of experimental physics. Yet, the mathematical beauty of string theory and its promise of unification were too compelling to ignore. And so the theory gained momentum, attracting some of the brightest minds in physics. Thus, the stage was set for a new paradigm in physics, one where tiny, vibrating strings took center stage. So what exactly does string theory propose? Well, in essence, string theory suggests that the universe is not made up of point-like particles as we have long believed. Instead, the theory proposes that the fundamental building blocks of the universe are tiny, one-dimensional strings. These strings are so minuscule that if an atom was the size of our solar system, a string would be as small as a tree on Earth. But what makes these strings truly fascinating is their vibrations. Each string vibrates at a different frequency, and it is these frequencies that give the strings their unique properties. In other words, what we perceive as different particles, electrons, quarks, neutrinos, are in fact the same strings, just vibrating at different frequencies. This is akin to different musical notes produced by the same guitar string depending on how it is plucked. This idea elegantly solves one of the major problems in physics, the incompatibility between general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles at the smallest scales. By replacing point-like particles with strings, string theory smooths out the mathematical inconsistencies that arise when you try to combine these two theories. But string theory doesn't stop there. It also introduces the concept of extra dimensions. You see, our everyday experience is limited to 3 spatial dimensions: length, width, and height. However, string theory suggests that there are additional dimensions curled up so small that we can't perceive them. These extra dimensions could provide the playground for strings to vibrate in ways that give rise to the diverse range of particles we observe. This idea of extra dimensions may seem far-fetched, but it's a critical part of string theory. In fact, for the mathematics of string theory to work out, we need no less than 10 dimensions, 9 spatial and 1 temporal. These extra dimensions might also explain some of the mysteries of the universe, like the nature of dark matter and dark energy. In string theory, therefore, the universe becomes a symphony of strings vibrating in multiple dimensions. It's a radically different way of looking at the universe, but one that could provide a unified description of all the fundamental forces of nature. And that's the beauty and allure of string theory. It's a bold step towards understanding the deepest mysteries of the universe. In string theory, the universe becomes a symphony of strings vibrating in multiple dimensions. But there isn't just one string theory, there are actually several versions. It's like having multiple ways to interpret a piece of classical music. Each interpretation brings its own unique flavor, but the fundamental notes remain the same. In our quest to understand the universe, we've encountered different versions of string theory, each contributing its own melody to the cosmic symphony. Let's delve into the trio of these versions: Type 1, Type 2, and heterotic strings. Type 1 string theory is the soloist of the group. It's the only one among the 5 that includes both open strings, those with 2 distinct endpoints, and closed strings, which loop back onto themselves. This unique feature allows Type 1 to produce a rich array of particles, including those that carry the force of gravity. Then we have Type 2 string theory, which is actually a duet of Type Tatry and Type Daiwebe. Both these versions exclusively feature closed strings, but they differ in the characteristics of their vibrations. Type 2A strings vibrate in a symmetric manner, whereas Type 2B strings vibrate asymmetrically. These different vibrational patterns give rise to different types of particles, lending a distinct flavor to each version. Lastly, we have the heterotic strings, which are like a fusion of 2 different musical genres. These strings are closed, but they vibrate in a peculiar way that blends characteristics of both Type 1 and Type 2 strings. This unique vibrational pattern allows heterotic strings to produce a diverse collection of particles, making them a rich and intricate part of the string theory landscape. Despite the differences, each version of string theory shares a common thread. They all propose that the universe is composed of tiny, vibrating strings. Each version might play a different tune, but they're all part of the same grand symphony, contributing to our understanding of the universe's fundamental nature. So while we explore these different versions of string theory, remember that they're all variations on a theme, each offering its own unique perspective on the cosmic dance of strings. Despite their differences, these versions all embody the same fundamental idea, that strings are the ultimate building blocks of the universe. String theory, however, is not without its critics. It's a world where the smallest entities are not particles, but minuscule vibrating strings of energy. Yet the boldness of this proposition has led to some controversies and criticisms. One of the most significant criticisms is the current lack of experimental evidence. As it stands, string theory exists in a realm that is currently inaccessible to experimental testing due to the incredibly small scale at which these strings are proposed to exist. It's like trying to spot a single grain of sand on a beach from 1,000 miles away, using only your naked eye. The technology and methodologies necessary to test these theories directly are simply not available to us at this time. Some critics argue that without experimental evidence, string theory is not a scientific theory at all, but merely a mathematical model. They argue that a scientific theory must be falsifiable, and string theory, lacking testability, does not meet this criterion. Another controversy revolves around the so-called landscape problem. This refers to the vast number of possible solutions to the equations of string theory, estimated to be around 10 to the power of 500. This immense number of solutions makes it difficult to predict anything specific about our universe, leading some to claim that string theory lacks predictive power. And then, there's the issue of extra dimensions. String theory proposes that there are more than the 3 spatial dimensions we experience in our daily lives. While this is a fascinating idea, it is also a source of controversy. How do these extra dimensions manifest themselves? Why don't we experience them? These are questions that string theory has yet to answer satisfactorily. Criticism also comes from within the scientific community itself. Some physicists argue that the focus on string theory has diverted resources and attention away from other promising areas of research. They worry that the allure of a unified theory might be leading us down a dead-end path. However, it's important to note that these criticisms don't necessarily mean that string theory is wrong. They simply highlight the challenges that need to be addressed as the theory evolves. And despite these controversies, many scientists remain optimistic about the potential of string theory. They see it not as a finished product, but as a work in progress, a stepping stone towards a deeper understanding of the universe. These challenges, while significant, do not diminish the potential of string theory to revolutionize our understanding of the universe. One of the most intriguing aspects of string theory is its implication for the concept of a multiverse. This is where our understanding of the universe takes a leap into the realm of the extraordinary. You see, string theory doesn't just stop at proposing that the fundamental entities of our universe are tiny vibrating strings. It goes further, suggesting that these strings vibrate in not just 3, but multiple dimensions. We're talking about dimensions beyond the 3 spatial ones we're used to: up and down, left and right, forward and backward, and the dimension of time. Now, here's where the multiverse comes in. The extra dimensions suggested by string theory could be compactified or curled up in a multitude of ways. Each unique configuration of these dimensions could give rise to a different set of physical laws, sort of like different settings on a cosmic game console. And that's not all. Each of these unique configurations could, in theory, represent its own universe existing alongside ours in a vast multiverse. Imagine the possibilities. There could be universes where gravity is weaker or stronger, where light travels at different speeds, or where entirely new laws of physics apply. Some of these universes might be eerily similar to our own, while others could be wildly different. However, it's important to remember that this idea of a multiverse is still speculative. While it's a fascinating consequence of string theory, we don't yet have any empirical evidence to support it. But it's an idea that has sparked a great deal of interest and debate within the scientific community. Some see it as a potential solution to some of the biggest puzzles in physics, while others view it with skepticism. Regardless of where one stands on the issue, there's no denying that the multiverse concept is a testament to the incredible potential of string theory. It invites us to imagine a cosmos far more complex and diverse than what we see around us. The idea of a multiverse, while speculative, opens up exciting new possibilities for our understanding of reality. The question remains, how can we test string theory? This is a conundrum that has been perplexing physicists for decades. The intricacies of string theory place it well beyond the reach of our current experimental capabilities, creating a significant hurdle. Testing string theory is no simple feat. The primary reason for this is scale. The strings proposed by the theory are so tiny, they are estimated to be about 100 billion times smaller than a proton. To put that into perspective, if a string were the size of an average tree, a proton would be approximately the size of the entire observable universe. So, how do we bridge this colossal gap? One potential avenue lies in high-energy physics. The Large Hadron Collider, for instance, probes the universe at incredibly small scales and high energies. If there are any effects from string theory to be found, they might just show up in these extreme conditions. Another possibility is through the study of cosmic strings, hypothetical topological defects in the fabric of the universe that could provide indirect evidence for string theory. These cosmic strings, if they exist, would create distinctive patterns in the cosmic microwave background radiation that we could potentially observe. A third avenue is through the study of black holes. String theory provides a unique perspective on the nature of black holes and their mysterious properties. If we can observe phenomena that align with these predictions, it could lend credence to string theory. However, it's important to note that these are just potential avenues. The reality is, we're still a long way from being able to definitively test string theory. It's a bit like trying to read a book in a dark room. We know the words are there, but we need more light to see them clearly. While we may not yet have direct evidence, the search for experimental confirmation of string theory continues. The quest for understanding our universe is a long and winding road, but with every step, we get a little closer to unveiling its profound mysteries. As we come to the end of our journey, let's recap what we've learned about string theory. We've delved into the fascinating world of theoretical physics, exploring the concept that the fundamental entities of our universe might not be point-like particles, but tiny, vibrating strings. We've discovered the different versions of string theory, each with its unique characteristics and implications. We've also faced the challenges and controversies surrounding this intriguing theory. The testability, the landscape problem, and the criticisms from within the scientific community. These are all significant hurdles that string theory needs to overcome. Not to forget, we've also discussed the concept of the multiverse, a staggering notion that our universe might just be one among an infinite number of universes, each with its own unique set of physical laws. Thank you for joining me on this exploration of string theory. Remember, the pursuit of knowledge is a never-ending journey,